Hi everyone, welcome to the logarithm functions review video. This is chapter 8 in the McGraw-Hill-Ryerson textbook that many of you are studying from here. Oh, wow. And this review video is going to be brief. If you want to look at the individual lessons from chapter 8, I'll put a little bit of a connection to that, a link to that. You can check those out anytime. But let's talk about logarithms. Okay, first of all, what is a logarithm? Well, a logarithm is the inverse of an exponential, and the use of it is really helpful in solving exponential equations. And we're going to get to that at the very end of this chapter, very end of this video, solving. Okay, so it's not a new concept, logarithms, but I want to just show you this graph here to help you understand the connection between exponential functions and logarithms. Okay, so here in blue, obviously, we have an exponential function, and remember the characteristics of exponential functions. When x is very largely negative, it's close to y equals 0, right? And there's an asymptote at y equals 0. As we move from left to the right, the graph starts to rise very slowly, passes through y equals 1, and then rises very sharply. That's the nature of an exponential, okay? So any situation where you have this sort of thing where it's a slow rise and all of a sudden it just takes off, like the spread of a global pandemic, let's just say, that's sort of an exponential function. And of course, obviously, in that case, we don't want it to go up to infinity. We want that curve to flatten, right? Buzz. 2020 here. Yes, we're in 2020, this video. So what's the inverse? Well, if you think inverse, you should remember, if you watched any of my videos, you should remember reverse, okay? So inverse means reverse. Reverse what? Reverse the x and y. So if you flip or reverse the x and y, what happens is you get a graph that behaves kind of oppositely of the exponential. So let's think about this. The exponential graph started on x equals, a large negative value for x, rose very slowly. Well, that's a large negative value for y. And it kind of begins to increase here, but it kind of diverges away from this axis very slowly, just like this one did up here. It goes through, the exponential goes through y equals 1. The log goes through x equals 1. The exponential, as x gets larger, it rises very sharply. Well, the log, as x gets larger, starts to flatten out. Okay? Starts to flatten out. So lots of opposites. Also notice the exponential, it doesn't ever dip down here in the negative for y. The log never dips over here in the negative for x. That's another important thing. Okay, so now that you've kind of got that idea, I know this logarithm thing looks really strange, but it is the opposite of an exponential. And so if you take the inverse of an exponential, you're going to get a log function. Now, I'm going to show you this real briefly here now. I'm going to come back to this a little bit later, but this is a bit of an explanation as to why logs are really important. And here also is the connection between an exponential and this log here being the inverse, which I will go over this in more detail a little bit later. Okay, so a couple other important things to remember is this. I'm going to zoom in here. This is from your textbook, so you've seen this before. But notice the base of an exponential function is this c value right here. Okay, that's the base. In a log statement, the base is down here. It's a subscript, and it's the log of something base something. Okay, over here. All right. Think about the log as an exponent. It's very important. So here's a logarithmic form. This is the exponent on the exponential. Okay, I've zoomed in too much there. It's getting pretty fuzzy there. So the logarithm, think about it as an exponent. Some logarithms will have a base that is c. So you might see something like this: log of 25 base 5. Okay, that is a logarithm, and if we're evaluating that, we are looking for what? An exponent. A logarithm, it can be thought of as an exponent. Where did I see that? Here we go. A logarithm, it's an exponent. So what exponent with this base gives me this value? Well, it's 5 to the power of 2. Okay, 5 to the power of 2. If we do not have a base stated, which if something looks like this, then that base is understood to be base 10 down here, the common logarithm. Okay, so it's basically 10 to what power? gives us 25. Okay? All right? Okay? So just think about that. That's the connection between logs and exponential functions. Here's the key ideas for 8.1. Okay, so the domain of a log function is everything greater than x. Okay, can't be in the negative x there. The range is all real values for y. It can go all the way down. And this doesn't flatten out really. It does keep expanding, but it just goes up real slowly. Yeah, okay. X-intercept of 1. Okay. All right, so here's some examples. And again, this is going to be a quick video, so I'm going to give you all the answers here. I'm just going to walk you through it. Okay, so let's say we are asked to evaluate a log. Well, remember that a log is an exponent. And so what we want to do is we want to focus on the base, and we want to ask ourselves, what exponent can I put on this base to give me this number? So it becomes very easy when you just kind of go, hey, 2 to the power of my value of this logarithm equals this value here. So that's what I always do. I always look at the base, and then I raise it to some power, and I let it equal this. So when you get to this point, 2 to the y equals 32, well, we know that y equals 5 in that case. Okay, so the logarithm of 32, that's how you read this, the logarithm of 32 base 2 is 5. Okay, so the log of 32 base 2, okay, 2 to the power of what equals 32. Okay, now over here, this one, again, 9 to the power of y equals the 5th root of 81. And you're going to look at that and you're going to say, oh boy, that's a little tricky. Nope, not tricky at all. Okay, we can write these with the same power, can't we? 81 is 9 squared. The 5th root is to the power of 1/5. Okay, this is all stuff that you should know already. If I simplify this just a little bit, a power raised to a power, we multiply. So look at what we have. We have two identical things, the same base. That means the exponents have to be equal, and sure enough, y is 2/5. Okay, so what this is saying is that the log of the 5th root of 81 with a base 9 is 2/5. So 9 to the power of 2/5 equals the 5th root of 81. All right. Okay. Next set of questions here. Determine the value of x. Again, we go back to the fact that this is the base, this is the exponent, and it has to equal this thing. 4 to the power of negative 2 equals x. No problem. That's 1 over 4 squared, 1 over 16. All right. So again, you could speak this out by saying the log of 1 over 16 with the base 4 is negative 2. That's what this all means. Over here, again, 16 to the power of negative 1/4 equals what? Well, you evaluate that. Let's get rid of the negative, drop that down to the denominator. To the power of 1/4, same as the 4th root of 16. Okay, the 4th root of 16 is 2. So that's 2 times 2 times 2 times 2 is 16. So x here equals 1/2. So that is the log of 1/2 with a base 16 is negative 1/4. All right, hope you guys are, I hope this is making sense. Hey, hope this is making sense. Again, watch the full videos if you need some more explanation. It's no big deal at all. Feel free to do that. A little note here that I put, this is important, that if you see this notation, f to the negative 1 of x, that kind of thing, that denotes inverse. Okay, so you're going to see that in your textbook and in your questions. All right, so that's 8.1. Let's talk about 8.2. 8.2 is transformations. Now we've been doing transformations this whole course, and we've been doing them on different functions. Well, it's the log's turn now. And one thing you can rest assured is that these parameters, like a and b and h and x, they do the exact same things as with the other functions. Okay, so let's just take a look here. The blue function is y equals log of x. Okay, that's your standard y equals log of x. And what we're going to do is we're going to try and figure out how do we get to the red function here. Well, if you take the key points, you can see that they are vertically separated by a factor of 3. Okay, so this was a 1, this is at 1, and then this one is at 3. This right over here, look at this. This looks to be about 1/3, and this is about 1. See? 1/3 times 3 is 1, and so on. You can go along and do that each time. Times 3, times 3, times 3, times 3. Okay? So there we go. We've got a, here a is 3, a vertical stretch. Now what happens if we go from this red one now to the turquoise one, okay? So the red graph to the turquoise. Well, here are our key points. There's a key point right there. And here's another key point. And notice they're on the same vertical. So it appears that this red graph has been squished up, right? Okay. So that's a horizontal compression. If all of the points have been changed by a factor of 1/2, because this is 10 and this is 5, right? Let's see, this is 4 and this over here would be 2. See, 1/2, everything's 1/2. So that means we have a b value of 2, right? That period length, if you want to think of it that way, 1 over b. Okay, so 1/2 is b is 2. All right, so we're just building here, right? So graph 3, okay, this again, we've got this graph and we are changing it to the purple graph now, okay? And it looks like our key points that are given, it looks like this is +1. And if we look at all these other points, right, +1, this is not multiply, this is simply add, same distance vertically, okay? And so what we do is we take this graph that we've already built and we just add 1 onto it, right? That's the horizontal, vertical translation. That's just moving it up, right? Not a stretch, it's just moving it up. Boom, like that, okay? So one last thing, let's talk about a horizontal translation. And of course, we remember that that is the h value here. So where do I get 4 from? Well, from this point to this point, it's 1, 2, 3, 4 units. See that? Also, the vertical asymptote is here at x equals 0. Now it's at x equals 4, a difference of 4 units. Every point is moved over 4 units. So that is, if it's moved right, we have to make sure that's a negative and the number of units. So you have to be real careful too with these brackets, okay? So notice back up here, the format is b bracket x minus h bracket. So those brackets are actually pretty important. So the b is 2 right here, the h is 4. So you can write it, you have to write it like this. Or if you expand this out within those brackets here, it's going to be 2x minus 8. Does that make sense? Okay. So again, got to be careful with this. H is not 8 here. H is not 8. Okay. H is 4. You have to factor this. H is 4. Okay. All right. I want to deal with something that could be considered a little bit tricky here, but I want you to notice something. I'm actually going to erase this and put it back later. Notice here that y equals log of 2x base 2 and y equals negative log of 2x base 2. This one is a horizontal reflection, right, about the x-axis. That makes sense. If a is negative, that means it flips this way, okay? But notice for both of these graphs that these log functions, they don't ever go into the negatives, okay? And so we do have to remember that if we have b equals a negative, if b is a negative, that should flip the graph over to the left, okay? I guess my big issue here, and this is why I'm doing this, is because if you ever check this on your calculator, like for example, let's do log of 25. Okay, there we go. That's 1.39. That means 10 to the power of 1.3979 equals 25. So what about log of negative 25? Well, your calculator is going to say that's a non-real answer. It's syntax error, whatever your calculator says. That's a problem. So we cannot take the negative, the logarithm of a negative number. We cannot. It does not exist. Why is that? Well, if you think about an exponential, what value of this exponent will make this side negative? Well, no value. It doesn't matter what y is. This over here will never be negative. Okay? So if y is very large, this is going to be very large. If y is negative, this is going to be small, not negative. Okay? That's very important. So that has implications for the inverse, for the log. Okay, so that means that x, or this value right here, cannot be negative in a log equation. We cannot take the log of a negative value. So what about this b? This looks pretty negative to me, doesn't it? Well, actually, this is only okay when x, right here, is negative. Because look at this. If you have the negative of a negative, that makes this overall positive. Okay, so I'll say that once again. If b is negative, that means x has to be negative. It has to be negative. So this graph right here, this looks bad because of the negative here, but as long as x is negative, then this whole thing becomes positive. So here we go. This is what this graph looks like. It looks just like this. These are the points, and that one's over there, and that one's over there, and see, it's a reflection about the y-axis, and it looks something like this right here. It's going to be tricky to do. Oh, awesome. That's a pretty good graph, actually. Okay, so it can be negative when b is negative. When b is negative and x is negative. See, if x is positive, that black graph does not exist over here. See? X cannot be positive in this case. All right, so I went in a little more detail than I had planned to do there, but anyways, I hope you're getting that. Okay. All right, for this graph right here, again, I have all the answers here on this review, so you can kind of skip through as much as you want, or put me on fast mode or whatever, so I can talk really fast or whatever, so you can get through this. But this blue graph, okay, how do we get this blue graph to the red graph? Well, it looks like this blue graph has been flipped about the x-axis. Awesome. So that means that we have to have a negative a value. And I've just sketched out what the negative of this blue graph would look like. It would be flipped exactly around there. Now to get to the red graph, because this point has not changed, we're not like actually sliding it down, we're actually stretching it. Okay? And if this is a -1, then this point right here is a -3. You guessed it. This is a factor of 3. So I have my negative and I have an a value of 3. So this is what this red graph looks like right here. All right, so for we just on 8.2? Yeah, 8.2, here's the key ideas. I'll let you take a quick look at that. I highlighted this because b can be less than 0 as long as x is also less than 0. So that's just a flip, okay? Here's another kind of a neat thing for you to remember. Only h can change the vertical asymptote. That's a slide left or right. And that's the only thing that changes the domain as well, which makes sense, okay? All right. And none of the parameters change the range, okay? None of the parameters change the range. It's always YER. 8.3, okay, here's where we get into the laws of logarithms. This doesn't have to take too long here, but this is just some, again, math is about patterns, right? Recognizing patterns and using those patterns for good, right? Or to using those in other situations. So here are some 3 main laws of logarithms. The first one is the product law. So let's say we have a logarithm of 20, okay? So the log of 20, well, that actually can be written as the log of one of its factors, let's just say 5, plus the log of 4, the other factor of 20, okay? So that's a law. I checked that out on the calculator, and I give you a little clipping here. So the log of 5 times 4 is the same as log of 5 plus log of 4. Exactly the same. So you can split this up, and of course, this could be, watch this, log of 10 plus what? Log of 2. That works as well. That's pretty cool, actually. That's pretty, and that may come in handy later. Well, I think it's cool anyways. You probably don't think it's cool. I think it's cool. All right. Quotient law. Quotient law. Very similar to the product law, except that we're talking about a quotient which is dividing. Okay? And the only difference is we subtract. Okay? We subtract. So the log of 5 divided by 4 is the same as log of 5 minus log of 4. Okay? And so on. I mean, log of 10 divided minus a log of 2, right? That sort of thing. All right, power law. This one is uber important, and we're going to be using this lots, and this actually gives the logarithm its effectiveness here in this chapter when solving exponential equations. This is kind of cool. If you have a power that you're taking the log of, you can write that as this. That exponent can actually come down out of the exponent position here, can come down as just a constant multiplier, which is super cool. And what that means is this: if we have the logarithm of 5 to the power of 4, that's the exact same as 4 times the logarithm of 5. Exactly the same. And that brings us to, like I said, the logarithm and its importance. over here. Now, before I get to this, there is one law that's not in your textbook that I think is super important. I think it should be. I don't know where you guys learn that. You learn it somewhere, or maybe just I teach it somewhere, but it's the change of base law. This is super important. If you have a logarithm and you have the value in here and you have the base here, you can rewrite that as a division of two separate logarithms. Very cool. The log of m base n is the same as the log of m base whatever divided by the log of n base whatever, as long as these are the same. So this is the final piece in really taking a good hard look at this. Again, here's exponential, okay? Exponential form, y equals some constant to the power of x. When you take the inverse of that, you flip x and y around, reverse. Inverse means reverse. And then you can take the log of both sides. Well, what does that do? I can use this power rule to bring y down as a multiplier. Then I can divide both sides by log of c. So I get y all by itself here. And then the final change of base law, or change of base formula here, says that when we have this situation, you can rewrite that as this right here. So the exponential, the inverse, can be rewritten as this log right here. Okay? And I know you're all thinking, wow, that's really going to change my life. I'm really glad I know that now. And you know what? It may change your life. I mean, you know, you never know. When I was your age, I didn't know I was going to be a math teacher. I mean, you know, so you might do this for the rest of your life. Who knows? Okay. I hope that doesn't make you sad. All right, let's do a couple more examples here with just exploring these properties. Okay, so I did letter A here. Again, it's just an example. If we have log of x times y over z, base 5, you can rewrite that as separate individual logarithms. I know that's pretty cool. So x times y becomes log of x plus log of y, right? The times becomes adding the logarithms. And then dividing by z here becomes minus log of z. So this right here is the same as this over here. D is a bit trickier, a little bit. Now I'll walk you through this. So again, I have x log of x cubed. I wrote that down here. And then now we're dividing, right? So that's where this minus comes in. And because this is going to be two separate logs, I'm going to make a brackets. I'm going to put brackets around there. And that's divided by log of y plus, because these are multiplied together, y times. And the square root of z can be written as z to the 1/2. Okay? So log of x cubed minus bracket log of y plus log of z to the 1/2. That's the first step. You can further simplify that by using another rule. That's the power rule. Remember, this 3 can come down in front. I get rid of the brackets, and this is going to be minus log y. This minus will distribute to be minus over here. And again, this 1/2 can come down in the front. See that? So there you go. That's how it can be simplified. And I just put a little check over here. Where did that go? That just disappeared. Did you see that? That's weird. This computer's acting up today. I'm going to rewrite that. Okay, take that. So I'm going to check this. I'm just going to put in values for x, y, and z. And on the left side, okay, that's what this equals right here. If I simplify this, that's 8 on top, 3 times square root of 4 is 2. So that's 8 over 6, okay? And then I put in the right side, what I determined over here, and I put them both into the calculator. And so, long story short, they both equal, look at this, the exact same value. That's awesome, okay? So you can take something and rewrite it a totally different way, and using these laws, and it'll always work. Always work. All right, another little different angle here of this. Use the laws of logarithms to simplify and evaluate each expression. So remember, if I have an addition of logarithms, that can be rewritten as a single logarithm where 8 and 9 are multiplied together. So that's where this comes from. A subtraction represents a division. So I'm dividing now by 2. Okay? 8 times 9 is 72 over 2. Well, I know what 72 over 2 is. That's 36. And then watch this. Log of 36 base 6. You can do that in your head. 6 to the power of what gives you 36? 2. 6 to the power of 2 equals 36. You see that? And I just took the liberty to do this on my calculator earlier as well. I just plugged this all in here, and guess what? It gave me 2. Okay, so that's using the laws of logarithms, and here they are again, along with the change of base law that I added here for you. And you can take a moment to take a look at that. Our final section is 8.4, and this again is where logarithms really prove their worth to us. If we have an exponential equation that we're trying to solve, and we cannot write the bases of the exponent of the powers as the same base, we can't write them with the same base, we're in trouble, right? Enter logarithms. So we're going to be able to solve exponential equations when the bases are not powers of one another. And we also have to, I just put a little highlight on this too, we have to check to make sure our answers are not extraneous, or make sure that they're allowed. And I'll show you what that means here. Okay, so in this little part of the lesson here, it asks us to use one of the laws of logarithms to rewrite the left side. Okay, that's going to be easy. I see the power law here. I'm going to write this as log of x squared. Okay, so log of x squared equals log of 36. That means that x squared has to equal 36. And you can solve that by regular algebra means, and you get x equals, because this is squared, it could be positive or negative 6. Let's check for that extraneous root. Let's make sure that both of these answers could be possible. And over here you see that I have included positive 6 in here, and sure enough, positive 6 works out. Left side equals the right side. Over here though, I've run into a problem right away, because look at this. I'm asked to take the logarithm of a negative value. If you remember from earlier in the video, that's bad. Cannot do that. This is undefined, and of course something that's undefined or not allowed does not equal an actual number here. So that means we have to stroke out x equals negative 6 as being an extraneous root, and our answer is x equals 6. Okay? Alright, so here's some examples that we can do along those lines, and we'll take a look at A right here. Notice that we have a log equation here, and we have the exact same log with the same base. So these two things are equal, and what that means is I can take this part of that equal thing and let it equal the corresponding part. And so 2x minus 1 equals 11, x equals 6, and this x equals 6 does not make either of these negative, so we're good to go there. Okay, so corresponding parts of equal things are also equal. Now B is a little trickier. Let me walk you through B. We have this 1 over here, right? So this is what I did. I took this log and I brought it over to the left side to make this. Log of 8x plus 4 minus log of x plus 1. Okay. Now I looked at that and I saw, hey, I'm subtracting logarithms, so I can rewrite that as a quotient. Okay. Now when I have a log on one side and just a value on the other, I can rewrite that, and I'll clean this up just a little bit for you. I can rewrite that as 10 to the power of 1 equals this whole thing. 10 to the power of 1 equals 8x plus 4 over x plus 1. That gets rid of my log, but it also, just gets me a regular algebraic thing, and no problem, right? So multiply x plus 1 by both sides, I get over here 10x plus 10 equals 8x plus 4. Combine my x's, combine my constant terms, I get x equals negative 3. Now the reason why I had that stroked out is because upon checking, watch this, if I put a negative 3 in for x here or a negative 3 in for x here, I get a negative value, and that cannot happen. I cannot have a negative, I can't take the log of a negative value, so that means that this answer is no good. So there's no other answers that work, so we have no solution here. And checking these things or solving these things graphically is another important thing. You kind of know how to do that. You would graph the left side here, y equals this, and then graph the right side, y equals this, and find out where the intersection point is. Okay. Now I actually did that for you already. Let's get over to Desmos. So there's a bunch of my videos you can watch. So here's Desmos, and look at this. Here's the first log, and here's the second side, the first left side and the right side. And notice on the graph over here that they don't intersect at all. Okay, no matter where you go, they do not intersect. That means there are no intersection points are no solutions. So, like I say, if you want to ever solve by graphing, you just graph the left side, you graph the right side, and you're good to go, and you solve for the intersection point. All right, here we go. Here's a case where we have an exponential and we're asked to solve, but 605 is not a power of 4. Cannot be written as a power of 4. 3 cannot be written as a power of 4, right? So here's where logarithms come in handy. So if I have 4x equals 605, I take the logarithm of both sides. Once I do that, I can use this power rule to get the x out of that exponent position, which is super, super important. Now I just divide both sides by log of 4, and log of 605 divided by log of 4 gives me a value of 4.62. So that means that 4 to the power of 4.62, probably the rest of the decimal there obviously, should equal 605. And that's something that you could check on your calculator. And let's see, I could do that right now. So 4 to the power of 4.62, and there's going to be more, so this is going to be pretty close. It should be close to 605. So if I used all the decimal places, that would be exactly 605. Okay. C is going to take you a little bit longer to do, but it's not impossible at all. So let me just try and walk through C. I take the logarithm of both sides. Here we go, log. What that does is it gets me this exponent, which is this expression, right, in the log, and this exponent also in a log, and I can bring those down out of the exponent position, and that's what we end up with down here. From here, I can expand, I can multiply, right? So 2x times log of 4 is 2x log of 4. Negative 1 times log of 4 is minus log 4. All right? So what I'm doing is I'm expanding here, it's the same thing to the right side. Okay? Now, the goal is to solve for x, so I have to get these x's together. I'm going to bring those terms together and bring those terms together over there. And now I've got this, okay? Where my x terms are all on the same side of the equation. I can factor an x out, which I did. What I'm left with is 2 log 4 minus log 3. Well, 2 log 4 is the same as log of 4 squared, isn't it? And so on. And here I've noticed that this is an adding of logarithms, so I can multiply 3 squared, which is 9, times 4 to give me 36. So you see, you break it down, and then you put it back together again. And I've also noticed over here that this is a subtraction. So I can rewrite this as log of 16 divided by 3, which is what I did down here. Divide both sides by that, and that is your value for x. And I thought I had a check for that. Let me just go through. This is some alternate notes here. Oh, come on now. Oh. Yeah. No, that's the other one. Oh, okay, that's the other one. Oh, goodness. Okay. I'm losing it. No problem. Everybody knows I'm losing it. Now it's just confirmed. Okay, so anyways, so log of 36 divided by, anyways, 2.14, trust me. All right? So using the logs of logarithms to solve. That's super, super important. This is super important. Okay? The final thing I'm going to show you here, this is the last thing. We haven't done really many word problems, so I'm just going to throw a word problem in there as a bit of a review, okay? One of the things that many real-world situations can be modeled with an exponential or a logarithmic. The general model for many problems involving exponential growth here, or decay, is this. The final quantity is equal to the initial quantity times the change factor to the power of the number of changes. So here's a problem that I made up here that's going to use this, okay? So let's say Mr. MathWell was 150 pounds, and he experienced a growth rate of 10% per year. Now that would probably be mass here, obviously. How many years would it take for his weight to reach 197? So this is the type of problem we can use logarithms to solve. We're going to write this as an exponential. So here's the future weight. Here's my initial weight, right here, the I. And the growth rate would be 1.1, right? If you gain 10%, you multiply by 1.1. And then to the power of n. So this is how many times. Now if this is 10% per year, this n is going to be number of years. So if you have a number in front of your power here, you might want to divide that off first. It's going to make things a bit easier. So just divide by 150 here, and you end up with 1.31 equals 1.1 to the power of n. Enter logarithms, because remember, we want to get this n out of the exponent position. We cannot solve for it while it's in there. So take the log of both sides, use that power rule to get the n down here. Now it's freed from its exponent position. Divide by both sides by log of 1.1, and we're up over here. So n equals log of 1.31 divided by log of 1.1, and you just do that on your calculator. You get n equals 2.8, which means that it would only take me 2.8 years to gain 47 pounds, which is not good. I'm going to have to reconsider what I'm eating, because I don't want to experience that. All right, so again, logarithms, the big deal is that they can be used to solve exponential equations. And the laws of logarithms and the graphs of logarithms, all that is important. So that's your little summary of Chapter 8, Logarithms, and I hope that helps. Good luck in your tests.